Now imagine you are in a casino and you just lost your semester fee at a stupid slot machine. As you're about to leave, this mysterious guy shows up telling you he has got a chance for you to win back your money. You ask how, and he answers,
You will toss a coin until it shows heads, and this will end the game. The pot of money you can win depends on the number of times you toss the coin. Each toss double the amount of money you win. If the coin was tossed once, you receive €1. If it was tossed twice, you receive €2. And if it was tossed 3 times, you receive 4, and so on. But you have to stop before the coin shows heads. Otherwise, you have to pay us the generated amount of coin tossed you played.
You quickly agree as you feel lucky and start flipping the coin 1, 2, 3 times. As you already tossed 9 times, you have the feeling to stop. The guy pressures you to keep going. 10 times would be more than the semester fee, but 9 times isn't the total amount you have lost yet. But how likely is it that you will actually make that happen? In order to find out, you want to make a quick estimation using the maximum likelihood to calculate this. Estimating the maximum likelihood is a method that determines the values for the parameters of a model. The values of the parameters are chosen in a way so that the result and the curves fit the data that was previously observed in the best possible way. To make it more comprehensible what the maximum likelihood does, take a look at this example. The blue dots are 10 previously observed measurements. We can see that the points are clustered around 10. So if we consider this to be a normally distributed data, we would expect that an estimation for our mean will be around 10. So which graph do you think is the closest to what the maximum likelihood would choose in order to fit our blue dot data the best? Yes, you are very right. It was the blue graph. So let's get back to flipping the coin. You take a pen and a piece of paper and you quickly calculate the maximum likelihood. We know that the maximum likelihood of the parameter of a Bernoulli distribution is the sum of all xi divided by n, where xi is equal to 1 or 0, 1 being a success and 0 a fail, and n is the total number of trials. So, in our example, the coin was tossed 9 times, and we got 9 tails. If we want to calculate an estimation of the probability of getting tails, we could have that n is 9, the total number of tosses, and x1, x2, x3 until x9 will all equal to 1, because all tosses were tails. That means that our maximum likelihood estimator in this case is 9 over 9, which is 1. Wow, you are so excited. The odds are definitely on your side. After all, 1 means it will happen. This basically means that you can always expect to get tails. Wait, what? Always tails? This can't be. There must be something you didn't think of. The problem with this estimation is that you only considered the data available and totally ignored the prior beliefs about the distribution. So you quickly grab another pen and piece of paper and calculate anew. So to overcome this issue, you use a sequential estimate to update the probability distribution of your parameters. What you do first is to assume that this distribution is flat, which means that all possible parameter values are equally likely to happen. This means that our parameter, the probability of getting tails, can be any real number from 0 to 1 with an equal chance. We represent this with a beta distribution with parameters alpha and beta both equal to 1. Now after the first coin toss, we will update our distribution like this. x1 means that it is our first coin toss, so to say. So if x1 is heads, x1 will be 0. We will have a new distribution with alpha equals 1 and beta equals 2. But we had 9 tosses with tails, so x1 will be 1, we will get a distribution with alpha equals 2 and beta equals 1. After that, for our second try, which is x2, our posterior becomes our prior, which means that after the first toss, this is the new distribution, that we expect our parameter to have the following distribution. Again, because our toss was tails in the beta distribution, beta becomes plus 1. Therefore, we have a beta 3 minus x1 and minus x2. So this will be repeated for all our tosses individual. Looks like. This is the new assumption for how the parameter is distributed. This parameter represents the probability of getting tails in a coin toss after we got 9 tails in our first 9 tosses. As expected, the value of our distribution function goes up when it approximates 1. That means that after observing that you had so many tails in a row, you can conclude that it is very likely that the coin is rigged towards tails and that the probability of getting tails is very high. That does not mean that the next toss will necessarily be tails, though just that the probability for it to happen is very, very high. So just to make it clear, for example, considering this new distribution we predicted, we can see that the probability of the value of our parameter is higher than 0.8. It is actually almost 90%. However, you must have been staring at the wall for some time because this mysterious guy interrupts your thoughts with a very loud cough.
So, are you going to play the next round or not?
Now tell me, would you? And don't let the gambler's fallacy get you. Please note that the coin flip paradox was only partly shown in this video and has not been explained to full extent. If interest or question persists, please ask your professor or tutor.